All right, last example. I promise I'll go through this one relatively quickly compared to the other ones at least. In this case, we're doing the same kind of thing where we have an inlet and an outlet. We just have a different piece of equipment. In this case, we have a compressor. And a compressor takes a fluid from a compressor is for a gas. It's taking it from a low pressure and bringing it to a high pressure by adding in work. So this is a 5 kilowatt compressor. This is a 5 kilowatt compressor. It's taking, again, these are all givens. It's taking a refrigerant R134A, which we have tables for R134A. It's a common refrigerant. It's taking it from minus 20 degrees Celsius and 50 kilopascal and a mass flow rate of, again, 0.1 kilograms per second. So we know something about the inlet. We know something about the outlet. We know that the pressure is 300 kPa. So we know the final outlet pressure. And we want to know the final outlet temperature and really the rest of that final outlet state. So we're going to start by our mass balance, right? The mass balance is easy. M2 minus m dot 1 equals 0. So m1 is equal to m2 is equal to m dot. Easy because we have just one inlet and one outlet. We'll start with the general energy balance. Do we have a delta H? Yes, we have an inlet and an outlet, and things are flowing, so we have delta H. Changes in kinetic energy. There probably will be velocity changes, but they'll tend to be quite small. Similar with potential energy. There will be potential energy changes, but they'll be quite small. Typically, these are insulated. It's not always small. For an ideal condenser, it would be small. And we have work going into our system because we plug in the condenser, so we're powering it. So we get the simplified energy balance. Of delta H dot is equal to minus W dot. We can break this delta H apart to a mass flow rate times the difference in enthalpy, and we'll leave W dot alone, right? The sign convention for W, we have a W, the absolute value is 5 kilowatts, but it's useful to figure out for this equation what the sign should be. Right, 5 kilowatts in means that we have a negative 5 kilowatts. And right, we're plugging in negative 5 into this equation. So we have, just for completeness, H2 minus H1 equals negative, and then a negative 5 kilowatts. H2 minus H1. So it's important to leave the negative sign in this energy, in the general energy balance equation, because that corrects for kind of our normal sign convention, right? The steam engine, heat in, work out. Okay, so this is 5 kilojoules per second. M dot is, just erase that here, M dot is 0.1 kilograms per second. So we can find H2 minus H1 is equal to 50 kilojoules per kilogram. We can look up H1. H1, we're going to be looking this up in our refrigerant tables. It's at minus 20 C and 50 kPa, a little bit on about half atmospheric pressure. And if we look that up, that's 388.82 kilojoules per kilogram. So we can plug that in and find H2. H2 is going to be 388.82 plus 50 kilojoules per kilogram. So that will be 438.82 kilojoules per kilogram. So now we're looking to find a pressure of 300 kPa and an enthalpy of 438.82. So we're going to be looking at that and finding what the temperature is. We should find that the temperature is about equal to 44 degrees Celsius. Okay, so if you've ever put your hand on a condenser or on a compressor that's working, you'll know that the compressor is getting hot. And these calculations bear that out, right? Our fluid is coming in at minus 20 C, and after we put in this work to compress it, we're up to 44 degrees Celsius, right, which is about 100 degrees Fahrenheit. So we go from basically 0 degrees Fahrenheit up to 100 degrees Fahrenheit as we go across this compressor. So that, again, kind of quick, make sure you look at and can find the right values for this and can find the right temperature value. This second one is a little bit harder just functionally to use the steam table, I think, at least, to find something like a pressure and an enthalpy. Functionally, you're doing the same thing. You're looking for, say, 300 kilopascals, and then you're looking at the enthalpies to see where you find 438.82. You'll have to do an interpolation in order to get that final temperature of 44 degrees. But this gives just one more example of how we can do energy balances on different pieces of equipment.